Hey everyone, Max here. Today I'm going to be talking about confidence intervals. For population proportions. Okay. And so this is actually going to be fairly straightforward, but let's start with that nice little formula that you probably haven't had. So we'll have a p hat right here. This p hat being our estimated, or essentially estimated mean, or a sample mean for a Bernoulli random variable. And if you recall, this is the number of successes over number of trials. Okay. This right here specifically is basically the sample size. Okay. Plus or minus, and then if you recall to our z confidence intervals, this will be a critical value. And then what we used to do, so this is not what we'll actually do, but you would then do a sigma over square root of n, right? What we'll actually do here is we'll replace the standard deviation with a standard deviation for a Bernoulli in the n. So that means right here, this becomes a p hat times a1 minus p hat over n square root. And now the tendency for a lot of students right here is to take this and put a p naught there. So don't do this. We are not hypothesis testing. When constructing confidence intervals. Okay. That's what a lot of people are tempted to do. They're tempted to put a p naught here, but you're not. This is just going to be your sample mean. And in the converse, a lot of people are tempted when they're doing hypothesis testing to do a p hat minus a p naught, minus a p naught over, and then they're tempted to do a p hat times a1 minus a p hat over n. Don't do this. We are assuming p naught is the true value. So p times 1 minus p is equal to p naught times. Okay. And these are the two mistakes that students really want to make when we're doing population proportions, even though computationally it's going to follow the same way as all the other confidence intervals and hypothesis tests. So let's work through a quick example. I don't think it'll take very long since confidence intervals tend to be fairly straightforward computationally. And if you recall, I had you all learn how to compute this z star. So you'll have to always compute that z star. Oh, there I go, making the mistake. What's happening? I don't know what's happening. Okay. And just notice, let me fix that, but the root goes over the n as well. It covers the whole thing. Okay, so let's go back to our coin. Let's suppose we flip a coin 100 times and get 62 heads. Suppose we assigned the value 1 to heads and the value 0 to tails. Find a 95% CI for P. So this is actually going to be fairly straightforward. What we'll end up doing is we'll just compute the p hat. The p hat will be 62 over 100, which is equal to 0.62. And then we actually know z star for a 95% confidence interval because that's actually one of the most common ones. That's just 1.96. Again, this is something you'll have to find. And we covered that when we were learning how to do confidence intervals for a z statistic. Okay, it'll follow the same way because we're using a z. So you'll do the whole normal distribution. This is your CI, and you find these values. Well, one of them, right? This is negative absolute value, z star. This is positive absolute value, z star. Okay. And we have that n, of course, is equal to 100. So our confidence interval just looks like this. Well, actually, I'll do it how I would like to do it. You can use the decimal if you'd like, but I personally would just put 62 over 100 plus or minus 1.96. Then 62 over 100 times 1 minus 62 over 100 over 100 square root, and you're done. That's it. You can simplify the numbers if you'd like, but that's essentially the confidence interval. And all the other examples will follow similarly. So that's how you find a confidence interval for a population proportion.